If you run an industrial plant, there is a silent mechanism actively draining your profit margins. Microscopic contaminants are suspended inside your degraded hydraulic fluid, causing invisible, systemic failures across the factory floor. Hydraulic oil typically accounts for less than 2% of a plant's operating budget, yet improper fluid condition is directly responsible for up to 70% of all hydraulic equipment failures. Executives treat this system as a blind spot, absorbing the cost of downtime and high scrap rates as normal business expenses. We need to restructure that maintenance budget. To get there, we will walk through a 4-step process: identifying the mechanical flaw causing this heat stress, diagnosing the invisible resin it leaves behind, deploying high-voltage extraction, and establishing a daily human control point. Preserving capital requires engineering hydraulic fluid as a core structural asset, rather than a disposable commodity. Step 1 is understanding the physical environment. The modern factory floor relies on a fragile thermodynamic balance. Over the last decade, equipment manufacturers prioritized smaller physical footprints to achieve better machine specifications on paper. By doing this, they introduced a silent operational bottleneck. They reduced hydraulic fluid reservoirs by up to 40%. Because the machine still demands the same violent force and immense pressure, the entire heat load was pushed onto a much smaller volume of oil. The fluid is left with drastically reduced recovery time. This extreme thermal stress forces the oil to degrade rapidly. Trapped heat breeds a sticky, sub-micron oxidative deposit. While it remains soluble at high temperatures, it precipitates as a hard resin the moment it hits the cooler zones of your machinery. Mechanical engineers call this varnish. This varnish aggressively coats highly sensitive internal mechanisms. When it attacks servo valves, internal mechanical friction spikes. Valves seize unpredictably, leading to heavy hysteresis and wild fluctuations in molding pressures. Uncalibrated pressure inside an injection molding machine destroys the structural integrity of the final physical product. It creates short shots, warping, and dimensional failures that ruin entire production batches. This chart shows the direct relationship between injection pressure and polymer leakage. When operators increase injection pressure to overcome internal friction, the leakage rate surges. At 150 megapascals, you lose up to 60 milliliters of polymer per hour directly at the nozzle. The costs of emergency servo valve replacements and soaring scrap rates are measurable symptoms of an underlying thermodynamic flaw. Step 2 requires fixing how we measure the problem. Relying on standard condition monitoring tests like viscosity and acid number gives maintenance managers a false sense of security. These traditional metrics completely miss soluble sub-micron resin. By the time a noticeable change appears in your fluid's viscosity, the microscopic particles have already coated your internal components, and the machine is on the verge of catastrophic failure. You need an exact metric for your fluid's propensity to form varnish. That requires a membrane patch colorimetry test, or MPC. A high value on this scale confirms heavy oxidative stress and a critical risk of deposit formation. You pair the MPC with a ruler voltammetry test. This measures the exact remaining lifespan of the fluid's primary and secondary antioxidants. When those antioxidant levels crash, varnish formation skyrockets. Upgrading your testing protocol to include these two specific metrics provides months of advance warning before a valve seizes. This shifts your entire maintenance operation from reactive scrambling to calculated predictive control. Step 3 is extraction. Most plants assume their standard mechanical filtration systems will protect their sensitive servo mechanisms. Against severe thermal stress, they fail completely. Because varnish remains highly soluble at elevated operating temperatures, these microscopic oxidative particles easily bypass traditional physical barriers. The solution is a restorative sub-micron electrostatic intervention. This is deployed directly to the factory floor as a mobile kidney loop service. It purifies the oil while the injection molding machine continues to operate at full capacity. Electrostatic oil cleaning applies controlled, high-voltage charges to the fluid. This electrical field physically attracts and strips the oxidative contaminants from the circulating oil. Notice the contrast. This active magnetic attraction pulls the threads out of the fluid, while the passive failure of a traditional mesh filter lets the exact same sub-micron particles slip right through. Implementing this specific high-voltage intervention neutralizes the manufacturer's architectural bottleneck. It extends your hydraulic fluid life up to 100,000 hours and drops unexpected equipment downtime by 70%. Step 4 brings us back to the factory floor. Data and electrostatic filtration must be paired with an early warning diagnostic checklist, executed daily by the technicians operating the machines. Technicians need to listen for unpredictable valve chatter and measure sudden slowdowns in clamping speed. Both of these indicate massive energy lost to static friction. This diagram outlines the interconnected causes of machine failure. A critical physical symptom your team must look for is liquid polymer leaking at the nozzle and sprue bushing junction, which is a direct result of excess system pressure. Operators must cross-reference their maintenance logs. When a component suddenly fails or leaks, check if it correlates with periods of elevated ambient factory temperatures or poor machine ventilation. Standardizing this daily human inspection enables the maintenance team to identify and resolve fluid issues before they cause a systemic shutdown. Restoring absolute fluid purity directly impacts your mechanical hardware. Internal servo mechanisms actuate smoothly, removing the friction that triggers unpredictable machine seizures. The data confirms that clean hydraulic fluid improves overall equipment effectiveness through precise molding, fewer short shots, and a drastic reduction in emergency valve replacements. Start the process today. Walk onto your production floor. Extract a 100 milliliter sample of fluid directly from the operating reservoir and order an MPC test. Halting the purchase of replacement parts for preventable failures is the single fastest way to protect and scale your factory's profit margins.